from the University of Tsukuba, Japan. I'll be talking about this work entitled Exploring Constraint Handling Techniques in Real-World Problems on MOEA with Limited Budget of Evaluations. This work is done with Felipe Vaz, Klaus Aranha, and Marcelo Ladeira in a collaboration with Brazil. So in this work, we introduce the three-step Constraint Handling Technique, CHT, to search through areas that violate constraints to then find near-optimal solutions that do not violate them. In this work, we want to answer three research questions. Can we improve the performance of MOEA when solving real-world problems with limited evaluations? How does the different CHT affect the performance of MOEA? And finally, how does the three-step CHT improve the performance of MOEA? Okay, our motivation for this work is that we are addressing most objective problems, and they are common problems with objectives that need to be optimized simultaneously. Finding good sets of solutions is a hard problem, and even harder in real-world problems. One of the reasons is that the Pareto forms of these problems are generally unknown or have a regular shape, and also that they have highly unfeasible objective space. Understand how different algorithms. So why exploring real-world problems? Our motivation here is that although there are many algorithms that we could use for that, fewer of them are evaluated in problems with constraints. And when they are, these constraints are too simple. So we don't really know how these algorithms behave when dealing with problems with complicated constraints. So that's why in this work, we focus on this kind of problems, real-world problems with complicated constraints. And for that, we choose to use MOEA. We choose MOEA because it's quite simple to change the traditional algorithm so that the MOEA now considers constraints and deal with them. Okay, so how does the three-step CHT work? It has three steps. The first one, no penalty is given to any solution. In the second one, small penalty is given to unfeasible solutions. And in the third one, high penalty is given to unfeasible solutions. In the first step, we give no penalty to any solution because we want the algorithm to explore the search space freely. We do that in the first quarter of the search. For some generations, to give MOEA the ability to explore the problem in question. Then we move to the second step because we want now to start selecting and giving priority to solutions that are feasible, because this is our end goal, feasible solutions. But we want to use information from good performing unfeasible solutions because they might help to find feasible and good performing solutions. We also do that. We do that second step in the second quarter of the search, and again to some generations only, to facilitate the transaction from the first step to the third. And I'll explain the third now. In this step, we highly penalize unfeasible solutions because we want to give preference to feasible and only feasible solutions. Yeah, well, that's our end goal. That's why we do that in the third and fourth quarters of the search, more generations, because we want to polish the final output of the algorithm. So why exploring unfeasible areas matter? So take a look on this image on the right. We have an unfeasible area here in red and one feasible area in white. Exploring unfeasible areas of the search space might help MOEA to get to better regions of this objective space. For example, if we allow MOEA to pass through this unfeasible area, not avoiding it, but accepting it as part of the progress, it will likely get to a good solution to S3 with more ease than it would if you had to avoid this area, conturn it, and get to S3. So how do we use CHT in MOEA? So we have the aggregation function when considering penalty. It substitutes the aggregation function from MOEA to consider constraints. We have the penalty factor that depends on the CHT technique, and we have the violation of a solution. The violation of a solution depends on the problem. So for each aggregation function that we had before, we change to this new one when considering the penalty and the violation. We move on to our comparison study. We compare 7 different CHTs. So the first two are the low and high value static. They have a penalty value that is kept constant throughout the search of the evolutionary progress. We have the mode staged that penalize solutions given how unfeasible they are. The more unfeasible a solution is, the higher the penalty gets. We have the slow and fast growth dynamic, CHTs. They increase the penalty value over generation, from small values to bigger values. Then we have the self-adaptive, CHT. It tries to keep the ratio of feasible and unfeasible solutions constant and determine the penalty to reach a good ratio of these types of solutions. Then we have the proposed one from this work, the 3-step CHT, that focus on get a high exploration of the search space in the first steps, and then to penalize heavily solutions that violate constraints. So in our comparison experiment, we consider MOED with the different 7 types of CHT and MOED with no constraint handling technique, the traditional algorithm, as a baseline. We use the hypervolume as our metric for evaluation, and the reference point depends on the type of problem we are considering. In the analytical real-world problems, the reference point is 1.1, repeated to the number of objectives. In the Mazda problem, a real-world simulation problem that we consider here, the reference point is 1.1 and 0. And in the moon landing problem, another simulation problem that we consider, the reference point is 1, 0, and 1. Our experiment parameters that we will highlight here are the computational budget. We kept it very small to 30,000 evaluations, and we repeat each algorithm with constraints for each problem 21 times. And also we consider the repetitions for MOED, the baseline. We have 6 real-world analytical problems: the bus truss design, the design of welded beams, discrete brake design, side impact design of car, conceptual submarine project, and water resource planning. And we have 2 real-world simulated problems. The Mazda benchmark problem, we called Mazda here, where the goal is to design Mazda cars. We have 2 objectives: to maximize the number of common parts to 3 different cars and minimize the total weight of the car. And we have the lunar landing site, we call it Moon. The goal is to select landing coordinates in the Moon, and where the objectives, we have 2 objectives: to minimize the number of continued days, minimize the inverse of total communication time, and minimize the tilt angle of the robot that lands in the Moon. These 2 real-world problems were proposed as competitions by the Japanese Evolutionary Society. Our experimental parameters are the traditional components of MOED, so we isolate the variants only to the CHTs, and we fine-tuned the parameters using the iRace package. And the parameters that we tuned were the crossover parameter, the mutation parameter, and the probability of using of the neighborhood. So these are the results of the analytical problems. We highlight that this is the mean hypervolume of 21 runs. We have results of MOED with no penalty, and with each different CHT we talked about before. So as you can see, the first main result is that not using CHT is not good for the performance of MOED, and that using any CHT, as long as you use one for these problems, it's good. And that the 3-stage was quite well. So it was the best in 3 problems and had a good performance on the other 2, in the other 3. Then we move to the simulated problems. Again, we have the mean hypervolume of over 21 runs. We again evaluate MOED with no penalty with the 7 different CHTs we talked about before. In the Mazda problem, we can see that most algorithms did not go to hypervolume, but the three-stage that we proposed was the one with the best results so far. And although it was good for the moon problem, the best one in this case was the fast-growing dynamics. So as we can see here from both of the tables that I showed, using CHT is good, but different CHT will perform better given the problem they are addressing. So let's take a look at the end time performance of MOED, given the different CHT techniques and MOED with no penalty. And in this case, we can see that the three-stage that we proposed is the one here. It takes a long time to start to have some performance, and only in the later stage that it improves the hypervolume quite fast. And this makes sense because at first we are accepting many of unfeasible solutions that are not taken into consideration for hypervolume calculation. So it's only after the generation 50 that we start to heavily penalize and remove them from the population. It takes some time to get to a population that has only feasible solutions, but then we get quite good ones, which shows that accepting unfeasible solutions, although can slow down the increasement of hypervolume, has good effects in terms of finding end solutions and feasible solutions. End time performance on the moon landing, our three-stage, which is this one, as we showed before, is not the best one, although it has very good values, unlikely the Mazda problem. After the first quarter of the search, when we just start to penalize the little solutions, we start to get an increment in hypervolume, indicating that this problem, we have a good mix of feasible and unfeasible regions. And the algorithm has a jump after we move to a high penalizing step that leads to increments of the performance, but not as fast as the fast growth dynamic that starts well in the first quarter and is one of the best. We are surprised by the results of the mode stage that was quite good and one of the best in the third quarter of the search, but then reduced the performance, which indicates that this problem is a quite complicated one as well in terms of the of regions that are unfeasible and feasible. Probably they are very mixed together. So conclusions of this work. As I talked before, using CHTs can be responsible for increments of hypervolume compared to MOED without penalty. The three-stage CHT that we proposed in this work and the dynamic CHT are good choices for finding optimal feasible solutions. The three-stage allows MOED to explore the search space while selecting optimal feasible solutions at the end of the run. So we first explore a lot and then we start to polish and find optimal feasible solutions. And for future works, we consider to improve the performance of MOED on these simulated real-world problems, because those were the hardest, as we saw before. Using MOED variants that consider resource allocation, because they are a hot topic. They are being widely explored in the last years in the literature, and they showed promising constant and increments on performance of MOED. Okay, so this is the end of my presentation. For more information, you can send me an email on both addresses that I put here. You can also access my webpage, and you can scan the QR code from my webpage or the code if you look on this image here.